All right, let's get started with Lesson 6, Reaction Mechanisms. Now, most reactions do not occur in a single step to convert reactants to products. Instead, there's usually a series or a sequence of individual steps that take place in order to convert the reactants into products. Now, these series or sequence of steps are known as the reaction mechanism. You can think of the reaction mechanism really as the pathway for the reaction. For instance, down below we have a reaction mechanism that includes two steps. Now, each of these steps, if we look at them closely, we can add them up and we can get the overall chemical reaction. So let's do that. Let's add up these two steps. So some of the materials that are in the steps will be eliminated from the overall reaction. If you look closely at N2O2, you'll see it's both a product and a reactant, and therefore we can get rid of them. And then at this point, once we've gotten rid of all of the chemicals or particles that we can eliminate, then we add up the steps, kind of like when we saw in Hess's law. And so here we have two NOs, so we can add those two NOs plus O2, and our product is going to be two NO2s, and that gives us the overall reaction from the individual elementary steps. All right. Oh, and by the way, that's each one of these steps that we see in a mechanism are known as elementary steps. Okay, they're those individual steps that make up the reaction mechanism. Now, it is important to understand, though, that a reaction mechanism and the individual elementary steps in that mechanism are completely theoretical. There's no way to actually 100% prove that we are correct. However, through experimental data, especially gathered by the rate law or rate expression for this reaction, we can come to a pretty good conclusion that our reaction mechanism is probably pretty much right. But again, it's just theoretical, and we're not absolutely 100% sure. All right? All right, there are three important vocabulary words that we need to understand in order to deal with reaction mechanisms. The first one is unimolecular, which essentially refers to that an elementary step involves one single reactant. So when you look at the elementary step, there should only be one reactant involved. We'll give you some examples here in a minute. Bimolecular simply means that the elementary step involves two reactant particles. And termolecular simply refers to an elementary step that includes three reactant particles. However, termolecular reactions are extremely rare. We hardly ever see termolecular at all. All right, another vocabulary word I'd like to introduce is the rate determining step. Now, the rate determining step, by definition, is the slowest step in the reaction mechanism. It is the rate determining step that is going to determine the overall rate of the reaction. In other words, the slowest step in the mechanism determines really how fast the reaction is going to occur. Think about it, a track analogy. When you're running a relay in track, the relay team is only as fast as really the slowest person on that team. And you can think of the same thing with a reaction mechanism. The slowest step is really going to dictate the rate of the chemical reaction. All right, so we're going to go over some example problems that you're going to see on the exam. and talk about some of the things that you're going to face and have to do with these reaction mechanisms. First of all, mostly you're always going to be given the reaction mechanism. Not all the time. Sometimes you will have to, they'll give you some clues and you'll have to try to put the reaction mechanism together. And we'll practice some of those in class. But for the most part, they're going to give you the reaction mechanism. And what they're going to ask for is to use the reaction mechanism to determine the rate law expression. Now, if you recall, we said that mostly to get the rate law expression, you have to be given experimental data. And then you have to solve the rate law using that experimental data. However, you can determine the rate law if you're given elementary steps in a reaction mechanism. Now, I'm going to clarify something. You can never determine the rate law from the overall reaction, ever. However, if you do have elementary steps, you can use those individual steps to determine the rate law in the order of the chemical reaction. All right? And so that's what we're going to do here. We're going to use this, for instance, this mechanism that we see here on this page in the two elementary steps in order to determine the rate law for this reaction. Okay? So the first thing I'm going to do is I'm actually going to determine the overall reaction for this mechanism. So if I look, I need to get rid of the 2 N2s, like so, and then add them up, 2 NOs plus O2s, produce 2 NO2s. All right, now the rate law can only include our 2 reactants. So the rate law is going to be written out as the rate constant times our first reactant to the X and our second reactant to the Y. Okay? Now, normally, if we have experimental data given to us, then we can use that to find X and Y. But since we're given the mechanism and these elementary steps, we can use that to determine the overall rate law. Now, the rate law is really going to be based on the slow step, the rate determining step, which is indicated here. Now, the good news is on the test, they will tell you which one is the slow step and which ones are the fast step. Always use the slow step in determining the rate law. All right, so if we look at step 2, which is our rate determining step, you will notice that it contains oxygen and N2O2. Now, O2 is one of our reactants. Because there's only one molecule of O2, it tells us right away that O2 is going to be to the first order. So Y is going to be 1 because there's only one O2 there. Now, let's pretend for a moment that there was actually 2 O2s. If there was 2 O2s in that rate determining step, then Y would actually be 2. All right? But since there's only one, it automatically tells us that it's our order for oxygen is going to be first order. Now, you can only do that if this is an elementary step. You cannot make that same reasoning if it's the overall reaction. All right? Now, so we know that automatically O2 is first order. So I'm going to go ahead and write that in my equation now. First order. Now, the hard thing now is that NO, which is also a reactant, is not in my rate determining step. But N2O2 is. But N2O2 is not a reactant. So what do? Well, you got to remember that NO2 was made in the first step. And NO2 is dependent upon NO reacting with each other to form NO2. So in reality, the production of N2O2 and how fast it's being produced is really dependent upon NO reacting with itself, NO. So therefore, to determine what NO's order is, we actually have to look at the first step. And since we got two of those NO's, therefore, our order for X must be 2. Second order, because we have two of them. Now again, you can only do this if these are elementary steps. We could not get this from the overall reaction. You can't just say because the coefficient is 2 in the overall reaction that NO is second order, or because O2 has a coefficient of 1 in the overall reaction, it's first order. Can't be done. It's just coincidence in this case that is the case. You have to look at the elementary steps in order to make that case work. All right? This is going to take some time to practice, so we're going to do some more here. Okay, so here's another one. Let's go ahead and add up the equation to give the overall rate law. What can we eliminate? We can eliminate NO3s. Can we get rid of anything else? I don't think so, okay? So we got 2 NO2s plus CO produces CO2 plus 2 NOs. That's our overall reaction. So the rate law must include both reactants, NO2 to the X times CO to the Y. Okay? Now, let's look at the rate determining step, which in this case is the first step. So the rate law has to be dependent only upon the first step. So if we look at the reactants in step 1, we will find that there are 2 NO2s. That tells us that NO2 must be second order. All right? Now, since CO is in the second step and CO is not dependent upon anything, CO has nothing to do with the rate of the reaction. Therefore, CO is going to be 0 order. The concentrations of changes of CO have no effect on the rate whatsoever because it's not part of the rate determining step. Therefore, the real rate law for this reaction is K NO2 to the second order. And this is going to be second order reaction overall. All right? Now, hopefully you see that the fact that CO is not part of the rate determining step and it's not determined it's not dependent upon anything in the first step, so therefore it has nothing to do with the rate of the reaction, so it must be 0 order. All right, let's look at example number 3 here. All right, let's go ahead and add up our reaction. We can get rid of the F's, and I think that's it. So we got 2 NO2s plus F2 produces 2 NO2F. Okay, there's the overall reaction. So the rate law must be written as K NO2 F2 Y and X. All right, the rate determining step again is the first step. So in the first step we have 1 NO, So therefore, automatically, X must be 1. And we have 1F, 2. Therefore, Y must be 1. And we don't worry about step 2 because it's the fast step. So therefore, our rate law is NO2 to the first and F2 to the first. And it is second order reaction. Because we add up 1 and 1 gives us second order. All right? Let us go to example 4. Okay, again, we need the overall reaction. We can get rid of NO3s. That's it. So we add up our 2 NOs plus our O2s. Gives us 2 NO2s. So the rate law must be NO X O2 Y. Okay? Now the second step is our slow step. It's the rate determining step. So we look at that first. It contains only 1 NO, so X must be 1. And it also contains NO3. Uh-oh, NO3 is not part of the rate law. It's not a real reactant. All right? However, we do produce NO3 in the first step. Well, we can only do that if NO in the first step and O2 react together. And so really, NO3's production, making NO3, is dependent on how fast NO and O2 react together. So in reality, we have to have another X because we have another NO. So really, X has to be 2 because we have that NO and that NO. Both are important in this reaction. All right, so really, X overall is 2. So really, X is second order. And oxygen, then, has got to be first order because there's only one of those. So therefore, the rate law must be NO2, O2 to the first. And the overall, it is third order overall. Because 2 plus 1 gives us 3. All right? I know this is not easy to completely understand. You may have to relook at this lecture video a couple times to really master this and really think about what I'm doing here. All right? And try this on your own and see if you can come to the same conclusion as I am. All right? Let's try one more together. Oh, in this one we have 3 steps now. Getting a little bit more challenging. But nevertheless, we still only have 1 slow step, which we should always have. And the slow step, of course, is the rate determining step. All right, so let's get an overall reaction first. All right, the first step indicates that we have a reversible reaction, represented by the double arrow. But that won't change anything, so don't worry about it. Just add up the reactions as you normally would. All right? So I see that I can get rid of NO3 there and NO3 there. I can get rid of the NO2 and the NO2. I can get rid of this oxygen and that oxygen. And that is all I can get rid of, I believe. Yep, so now all I can do is add everything up. So I'm going to get 2 N2O5s, and that's going to produce 4 NO2s plus an O2. So in this case, I only have 1 reactant. So the rate law is equal to K N2O5 X. Okay, so let's look at our X value. Well, in the slow step, neither one of our reactants at all are in our overall reaction. So therefore, neither one of these can be determined in our rate law. But we do know that both of these reactants are dependent upon N2O5 breaking down and making them. So therefore, we really have to understand that N2O5 is the dominating factor that's going to determine the rate here, because N2O5 breaks down to form these two products, which are then used in our next step. They need to react. All right, so these two will not react in the second step until we make them in the first step. So therefore, it's all dependent on N2O5. So N2O5, because there's only one of them, tells us that X is 1. Therefore, the rate law N2O5 is first order. And this is a first order reaction overall. All right? So there's 5 examples. Again, we'll practice this in class. But I would study this really well. Get familiar with these reaction mechanisms, and come with questions to class. And that is it for now.